Hello, in this video, we are going to share the paper analysis of the increased and decreased algorithms for congestion avoidance in computer networks. My name is Xiangyu Han, and I'm working with my partner Ishvik. To begin with, let me share the difference between congestion control and congestion avoidance. Network performance changes as a function of the network load. If we plot the throughput and response time versus the load, there are two remarkable points. The first one is cliff, where the throughput falls off rapidly after this point and response time increases drastically. The second one is knee. After this point, the increase in the throughput is small, but the increase in the response time is significant. In this paper, a congestion control scheme tries to keep the network operating in the zone to the left of the cliff, while a congestion avoidance scheme allows the network to oscillate at the knee. In either case, oh no, sorry for that. My screen go dim. I think this is because I blocked the distance sensor. A little bit terrible, but let me see if this works. Let's go back to the start.
Yeah, fine.
Okay, 3, 2, 1, go. Hello. In this video, we are going to share the paper analysis of the increase and decrease algorithms for congestion avoidance in computer networks. My name is Xiangyu Han, and I'm working with my partner Ishvik. To begin with, let me share the difference between congestion control and congestion avoidance. Network performance changes as a function of the network load. If we plot the throughput and response time versus the load, there are two remarkable points. The first one is cliff, where the throughput falls off rapidly after this point and response time increases drastically. The second is knee. After this point, the increase in the throughput is small, but the increase in the response time is significant. In this paper, a congestion control scheme tries to keep the network operating in the zone to the left of the cliff, while a congestion avoidance scheme allows the network to oscillate at the knee. In either case, the algorithm will adjust the sending window or rate as the total load on the system changes, which we call the increase and decrease algorithm. This paper focuses on the congestion avoidance to ensure user requests are always granted. Briefly, we assume a simplified binary feedback model for the increase or decrease algorithm. There is a single shared bottleneck resource. The system is discrete and synchronous. Most importantly, the congestion state of the system is determined by the number of packets in the system and is represented by a binary signal that indicates either overloaded or underutilized. Every user receives this signal and applies its control accordingly. The notations are as follows. During time slot t, the ith user's load is this one, xi t. The system determines its load level and sends a binary feedback yt. The user then changes their demands for the next time slot t plus 1 as a function of its current load and yt. Though other schemes exist, here we focus on linear controls. That is, xi at time t plus 1 is equal to a plus b times xi at time t. The signal y is binary, so we have two cases and four parameters, ai, ad, bi, bd. In order to evaluate the effectiveness of the algorithm, now let's introduce a set of criteria. Firstly, we want efficiency. By efficiency, we mean that the load must be as close to the knee point as possible, as described in this equation. The next one is fairness. In this paper, the fairness is quantified as the square of the sum of all loads divided by n times the sum of each user's load squared. This index comes with several desirable properties. It's bounded between 0 and 1. If the allocation is totally fair, that is, every xi is the same, the index will be 1. Otherwise, if it's totally unfair, that is, only one user is occupying the whole resources, the index will be 1 divided by n, which is 0 in the limit as n tends to infinity. Thirdly, the system is distributed. Users only have the binary feedback. They never know other information like the number of users or the total available resources. Lastly, the algorithm must converge, and this is not the only requirement. The time to converge and the size of oscillations to be small. Thus, the controls are more responsive and more smooth. Those equations are a bit hard to understand, so in this slide, I will provide a two-user example. Two-user resource allocation can be represented as a point x1, x2 in a two-dimensional space. For efficient allocation, we have x1 plus x2 equals to x goal, which is shown as the efficiency line. For fair allocation, we have x1 equals to x2, which corresponds to the fairness line. Here we consider two basic examples. One is additive increase or decrease. On the vector representation, this will move the point alongside a 45-degree line. The other is multiplicative increase or decrease. This will move the point along the line between the origin and the point. Remember our index of fairness. If each xi is multiplied by some b, the index remains unchanged. As a result, all the points on the line between the origin and a given point will share the same fairness index. Effectively, this means that multiplicative increase and decrease alone will never change the fairness.
Uh, I'll now talk about the constraints in some more details and try to arrive at an increase-decrease policy where we converge for fairness and efficiency and satisfy the distributedness constraint as well. So for the starting with fairness, the fairness must improve in at least one of increase and decrease, and it should not degrade in either of them. This results in the following two sets of equations. For both increase and decrease, the fairness at time t plus 1 must be greater than or equal to the fairness at time t. And for at least one of them, we can get rid of the equality sign. So the fairness at time t plus 1 should be strictly greater than the fairness at time t. Solving these constraints leads us to the following set of conditions. These conditions effectively boil down to the fact that the sign of additive component and multiplicative component of increase should be the same and similar, and the case for the decrease is also same. Also, one of the additive components of increase and decrease should be greater than zero. For efficiency constraint, the feedback should be negative. This means that if yt is 0, that is increased, the total load at time t plus 1 should be greater than the total load at time t. If yt is 1, that is decreased, the total load at time t plus 1 should be smaller than the total load at time t. Now, if we combine the efficiency and distributedness property, we can arrive at a stricter condition which says that if the feedback is increased, the for each individual user, the load at time t plus 1 should be greater than the load at time t. And if the feedback is decreased, the for each individual user, the load at time t plus 1 should be smaller than the load at time t. Substituting additive and multiplicative components in these equations leads us to the following set of equations, and one of like these equations are satisfied by the following constraints. So here we basically have the additive component of increase should be greater than 0. The multiplicative component of increase should be greater than or equal to 1. The additive component of decrease is 0, and the multiplicative component of decrease lies between 0 and 1. These constraints also satisfy the fairness criteria where the components of increase have the same sign and the components of decrease also have the same sign. Also, one of the additive components is non-zero. So what do these constraints actually mean? Uh, since the additive component of decrease is zero, we can say that the decrease policy should also always be multiplicative. And since the additive component is of increase is always non-zero and positive, we can say that the increase policy always has an additive component. There can also be a multiplicative component, and if that is true, it should be greater than one. I'll now try to explain these sets of constraints using the vector representation. So first we'll focus on the first figure, which specifies the fairness constraints. So as mentioned earlier, uh, the two lines going through the origin represent the same fairness line, and we want to be and for fairness to either improve or to remain the same, we want to be in the shaded region. Now moving on to the efficiency property, uh, we have two important lines here. First, the a is equal to 0 line represents the multiplicative decrease line, and the b is equal to 1 line, which is the 45-degree line, represents the additive increase only line. The shaded region represents the area where we have both the additive component and the multiplicative component. Now, if we combine these two constraints, we can only decrease along the lines going through the origin. This means that the decrease policy should always be multiplicative. Uh, we have already talked about multiplicative decrease. Now let's focus on the increase part. So again, we have two sets of lines here. One is the line going through the origin, which is the multiplicative increase only line, and the other is the 45-degree line, which is the additive increase only line. The shaded region represents both additive increase as well as multiplicative increase. And as we can see from the figure, like if we are in this region, we are moving closer towards the efficiency line, as well as we are not degrading the fairness, so the fairness will either improve or remain the same. So here we have the overall picture, where the increase is additive in nature and the decrease is multiplicative in nature. So with increase, we improve the fairness and we move closer towards the efficiency line. And with decrease, the fairness remains the same, but we satisfy the efficiency criteria. The paper also talks about like how optimally we can converge to efficiency, and so basically how we can optimize the additive and multiplicative components for responsiveness and smoothness. So for responsiveness, we care about the time to converge, and the paper shows that it is a decreasing function of additive and multiplicative components. For smoothness, we care about the size of oscillations, and it is an increasing function of the multiplicative and additive components. So we can see that there exists a trade-off between responsiveness and smoothness, and we sort of cannot achieve the best of both worlds. Uh, Finally, I'll talk about some of the limitations of this paper. The paper assumes instantaneous feedback. So as the feedback delay increases, the feedback will become less valuable and the performance worsens. The analysis also assumes synchronous operation. So if the feedback delay or the frequency are drastically different between different users, the convergence cannot be guaranteed. That's it for the presentation. Thank you.